In logic and proof theory, natural deduction is a kind of proof calculus in which logical reasoning is expressed by inference rules closely related to the natural way of reasoning. This contrasts with the axiomatic systems, which instead use axioms as much as possible to express the logical laws of deductive reasoning. Motivation. Natural deduction grew out of a context of dissatisfaction with the axiomatizations of deductive reasoning common to the systems of Hilbert, Frege, and Russell. Such axiomatizations were most famously used by Russell and Whitehead in their mathematical treatise Principia Mathematica, spurred on by a series of seminars in Poland in 1926 by Łukasiewicz that advocated a more natural treatment of logic. Jaskowski made the earliest attempts at defining a more natural deduction, first in 1929 using a diagrammatic notation, and later updating his proposal in a sequence of papers in 1934 and 1935. His proposals led to different notations such as Fitch-style calculus or Supper's method, of which e.g. Lehmann gave a variant called System L. Natural deduction in its modern form was independently proposed by the German mathematician Gentzen in 1934. In a dissertation delivered to the Faculty of Mathematical Sciences of the University of Göttingen, the term natural deduction was coined in that paper. Ich wollte nun zunächst einmal einen Formalismus aufstellen, der dem wirklichen Schließen möglichst nahe kommt. So ergab sich ein Kalkül des nachlichen Schließens. Gentzen was motivated by a desire to establish the consistency of number theory. He was unable to prove the main result required for the consistency result, the cut elimination theorem, the Hauptsatz, directly for natural deduction. For this reason he introduced his alternative system, the sequent calculus, for which he proved the Hauptsatz both for classical and intuitionistic logic. In a series of seminars in 1961 and 1962, Pravitz gave a comprehensive summary of natural deduction calculi, and transported much of Jentzen's work with sequent calculi into the natural deduction framework. His 1965 monograph Natural Deduction, a proof theoretical study, was to become a reference work on natural deduction, and included applications for modal and second-order logic. In natural deduction, a proposition is deduced from a collection of premises by applying inference rules repeatedly. The system presented in this article is a minor variation of Jentzen's or Pravitz's formulation, but with a closer adherence to Martin Loft's description of logical judgments in connectives, judgments and propositions. A judgment is something that is knowable, that is, an object of knowledge. It is evident if one in fact knows it. Thus, "it is raining" is a judgment, which is evident for the one who knows that it is actually raining. In this case, one may readily find evidence for the judgment by looking outside the window or stepping out of the house. In mathematical logic, however, evidence is often not as directly observable, but rather deduced from more basic evident judgments. The process of deduction is what constitutes a proof. In other words, a judgment is evident if one has a proof for it. The most important judgments in logic are of the form, A is true. The letter A stands for any expression representing a proposition. The truth judgments thus require a more primitive judgment. A is a proposition. Many other judgments have been studied. For example, A is false, A is true at time t, A is necessarily true, or A is possibly true. The program M has type tau, A is achievable from the available resources, and many others. To start with, we shall concern ourselves with the simplest two judgments: A is a proposition, and A is true, abbreviated as a prop and a true, respectively. The judgment, a prop, defines the structure of valid proofs of A, which in turn defines the structure of propositions. For this reason, the inference rules for this judgment are sometimes known as formation rules. To illustrate, if we have two propositions A and B, then we form the compound proposition A and B, written symbolically as We can write this in the form of an inference rule, where the parentheses are omitted to make the inference rule more succinct. This inference rule is schematic. A and B can be instantiated with any expression. The general form of an inference rule is, where each is a judgment and the inference rule is named name. The judgments above the line are known as premises, and those below the line are conclusions. Other common logical propositions are disjunction, implication, and falsehood is true then B is true. In logic, one says, assuming A is true, we show that B is true. In other words, the judgment, be true, depends on the assumed judgment, a true. This is a hypothetical derivation, which we write as follows. The interpretation is, be true is derivable from A true. Of course, in this specific example we actually know the derivation of be true from a true. But in general we may not a priori know the derivation. The general form of a hypothetical derivation is, each hypothetical derivation has a collection of antecedent derivations written on the top line, and a succedent judgment written on the bottom line. Each of the premises may itself be a hypothetical derivation. The notion of hypothetical judgment is internalized as the connective of implication. The introduction and elimination rules are as follows. In the introduction rule, the antecedent named U is discharged in the conclusion. This is a mechanism for delimiting the scope of the hypothesis. Its sole reason for existence is to establish be true. It cannot be used for any other purpose, and in particular, it cannot be used below the introduction. As an example, consider the derivation of A true. This full derivation has no unsatisfied premises, however, sub-derivations are hypothetical. For instance, the derivation of be true is hypothetical with antecedent a true. With hypothetical derivations, we can now write the elimination rule for disjunction. In words, if A B is true, and we can derive C true both from A true and from B true, then C is indeed true. Note that this rule does not commit to either A true or B true. In the 0 case, i.e., for falsehood, we obtain the following elimination rule. This is read as, if falsehood is true, then any proposition C is true. Negation is similar to implication. The introduction rule discharges both the name of the hypothesis U, and the succedent P, i.e., the proposition P must not occur in the conclusion A. Since these rules are schematic, the interpretation of the introduction rule is, if from A true, we can derive for every proposition P that P true, then A must be false, i.e., not A true. For the elimination, if both A and not A are shown to be true, then there is a contradiction, in which case every proposition C is true. Because the rules for implication and negation are so similar, it should be fairly easy to see that not A and A are equivalent, i.e., each is derivable from the other. Consistency, completeness, and normal forms. A theory is said to be consistent if falsehood is not provable and is complete if every theorem is provable using the inference rules of the logic. These are statements about the entire logic, and are usually tied to some notion of a model. However, there are local notions of consistency and completeness that are purely syntactic checks on the inference rules, and require no appeals to models. The first of these is local consistency, also known as local reducibility, which says that any derivation containing an introduction of a connective followed immediately by its elimination can be turned into an equivalent derivation without this detour. It is a check on the strength of the elimination rules. They must not be so strong that they include knowledge not already contained in its premises. As an example, consider conjunctions. Duly, local completeness says that the elimination rules are strong enough to decompose a connective into the form suitable for its introduction rule. Again for conjunctions, these notions correspond exactly to beta reduction and eta conversion in the lambda calculus, using the Curry-Howard isomorphism. By local completeness, we see that every derivation can be converted to an equivalent derivation where the principal connective is introduced. In fact, if the entire derivation obeys this ordering of eliminations followed by introductions, then it is said to be normal. In a normal derivation, all eliminations happen above introductions. In most logics, every derivation has an equivalent normal derivation, called a normal form. The existence of normal forms is generally hard to prove using natural deduction alone, though such accounts do exist in the literature, most notably by Dag Pravits in 1961. It is much easier to show this indirectly by means of a cut-free sequent calculus presentation. First and higher-order extensions. The logic of the earlier section is an example of a single-sorted logic, i.e., a logic with a single kind of object. Propositions. Many extensions of this simple framework have been proposed. In this section we will extend it with a second sort of individuals or terms. More precisely, we will add a new kind of judgment. T is a term, where T is schematic. We shall fix a countable set V of variables, another countable set F of function symbols, and construct terms as follows. For propositions, we consider a third countable set P of predicates, and define atomic predicates over terms with the following formation rule. In addition, we add a pair of quantified propositions, universal and existential. These quantified propositions have the following introduction and elimination rules. In these rules, the notation T, X, A stands for the substitution of T for every instance of X in A. Avoiding capture, see the article on lambda calculus for more detail about this standard operation. As before, the superscripts on the name stand for the components that are discharged. The term cannot occur in the conclusion of I, and the hypotheses named U and V and E are localized to the second premise in a hypothetical derivation. Although the propositional logic of earlier sections was decidable, adding the quantifiers makes the logic undecidable. So far the quantified extensions are first order. They distinguish propositions from the kinds of objects quantified over. Higher order logic takes a different approach and has only a single sort of propositions. The quantifiers have as the domain of quantification the very same sort of propositions, as reflected in the formation rules. A discussion of the introduction and elimination forms for higher-order logic is beyond the scope of this article. It is possible to be in between first-order and higher-order logics. For example, second-order logic has two kinds of propositions, one kind quantifying over terms, and the second kind quantifying over propositions of the first kind. Different presentations of natural deduction. Tree-like presentations, Jensen's discharging annotations used to internalize hypothetical judgments can be avoided by representing proofs as a tree of sequence gamma A instead of a tree of A true judgments. Sequential presentations, Jaskowski's representations of natural deduction led to different notations such as Fitch-style calculus or Supper's method, of which Lemon gave a variant called System L. Such presentation systems, which are more accurately described as tabular, include the following. 1940. In a textbook, Quine indicated antecedent dependencies by line numbers in square brackets, anticipating Supper's 1957 line number notation. 1950. In a textbook, Quine demonstrated a method of using one or more asterisks to the left of each line of proof to indicate dependencies. This is equivalent to Klein's vertical bars. 1957. An introduction to practical logic theorem proving in a textbook by Suppers. This indicated dependencies by line numbers at the left of each line. 1963. Stoll uses sets of line numbers to indicate antecedent dependencies of the lines of sequential logical arguments based on natural deduction. Inference rules. 1965. The entire textbook by Lemon is an introduction to logic proofs using a method based on that of Suppers. 1967. In a textbook, Klein briefly demonstrated two kinds of practical logic proofs. One system using explicit quotations of antecedent propositions on the left of each line. the other system using vertical bar lines on the left to indicate dependencies.